So let's start where we left off. Gauss Law. So 7 applications of Gauss Law. So the first one is, see, all the applications involve finding the electric field. So first one is electric field of point charge. Which is also, we end up verifying Coulomb's law. So, yeah, the first application is finding the electric field. I told you, right, we use Gauss law to find electric field at a point. So if you want to find electric field at a point due to a point charge, so let us say this is a point charge. The step is same for every case. Draw a Gaussian surface. So Gaussian surface has to be symmetric to the charge distribution. So since it's a point, the symmetric surface is a spherical surface, with the center of the sphere located at the location of the point charge. So
the point charge, the point of interest should have the surface. Point of interest.
Yes. So suppose I want to know the location of the electric field at this point P. So this is the position vector R, and the electric field at this position will also be in this direction.
Electric field will be this direction.
Along the radius, right? So it will be along the position vector.
Position vector.
Yes, if there is too much noise, it won't be clear for you when you listen to the video. So electric field is in the direction of position vector. So whichever point you take, everywhere it will be the same story.
Okay.
Is it not? Whichever point you take, the position vector and the electric field vector will be in the same direction. So now if you take an area element, if you take a small area element here, that area element will have the area vector also along the R vector, because the normal to the area vector will be along the radius. Normal to the area vector. Area vector is a small piece on the surface of this spherical surface, right? The small piece on that, the perpendicular will be along the radius. Radius is normal to the surface.
Yeah.
So area vector is also parallel to the electric field vector. If you take any surface, any small area on the surface, the area vector is perpendicular to the surface. Imagine my hand is the sphere. Area vector is here. It's perpendicular to the surface.
Yes.
So the position vector is also perpendicular to the surface.
Yeah.
Which means they are parallel to each other.
Yes.
So now the flux through each small area element which I take is given by, so d phi so the small flux which is passing through the small area element dA is given by E dot dA. So the total flux is given by the integral over the entire surface
Integrate.
E dot dA. Agreed? And by Gauss law, the flux to any closed surface is supposed to be equal to the charge enclosed divided by the epsilon naught. This is Gauss law. Agreed? So now E dot dA, let us expand. Since E and dA are in the same direction,
Probably dq rather small.
dA refers to the small area element over which the electric field does not change. dA is that small area element over which the electric field is not able to change because it's so tiny. So this will become
E integral of D.
E dA cos theta, and this cos theta will be 1 because theta is 0. So this will become EDA, and everywhere if you see on the surface, the magnitude of electric field will be different or same. Use your knowledge.
What?
Every point on this spherical surface is equidistant from the charge. And electric field varies with distance. If distance is same, electric field magnitude will be same. So E in this integral is a constant. So E will come out of the integral. E to integral of dA.
Which is theta is angle between
The E vector and the area vector. And that is 0 everywhere. Even if you take an area vector here, the dA vector will be like this, the E vector will be like this. So the angle is always 0 everywhere. So now integral over the closed surface of all the small area elements making up this entire surface will give me the total surface. And total surface area of a sphere, we know the formula. What is it?
4 pi r square.
Very good. So E into 4 pi r square. And integral of the dA. Total surface integral of dA we know, right? Surface area of the sphere. Surface area of the sphere is 4 pi r square. So that is supposed to be equal to Q by epsilon naught. The charge enclosed is only Q. So now you can solve for electric field. So electric field is 1 by 4 pi epsilon naught into Q by r square, which is your Coulomb's law.
Oh my lord.
Isn't it amazing?
No.
How is it not amazing? You started with something and you ended with what you already know. It's like you start with a lump of clay and then you end up with a pot. But this is something you knew. But it's hiding in this.
Why did you do this?
Huh? But this was not apparent here, right? In this form it was not apparent. No, what I'm saying is two apparently two things which appear to be different. Can I erase? Hurry up. Yes.
What's the second last step?
What is this step?
Yeah.
The area integral is the total surface area. Total surface area of a sphere is 4 pi r square. That's it. And this step is following here. Equal to Q by epsilon naught. In Gauss law, the statement is the total flux through a closed surface is equal to Q by epsilon naught, where Q is the charge inside the closed surface. Okay? Epsilon naught is permittivity of free space, it's a constant. Okay, I'm going to erase. No second. Please be quick. Okay, let's change the title. Because every point on the Gaussian surface is same distance from the charge. Electric field varies with distance. Okay? Now electric field of infinite line of charge. Now the second application is to find the electric field due to an infinite line of charge. Imagine you have a line of charge which extends till infinity, both sides. So what kind of electric field will it set up in its surroundings?
Electric field due to
Infinite line of charge.
what is infinite line of charge?
No, I'm changing the title slowly. See, we have to finish 7 applications. Come on,
Today?
cooperate.
Today?
Yes.
Chalo. Ambitious.
Aim for the stars. You might want to.
Jaldi.
So those who missed the class yesterday, please watch the videos. It's all updated in the website.
Yes, sir.
You know, there's this thing called live streaming. It would be really useful.
Why do you need live streaming when you can be live present here?
Like, you can be multitasking.
We can ask house to live chat.
It's okay, you watch it offline and then infinite line of charge.
So, इसमें chapter था ना?
किसके बाद? Yes, Gauss Law chapter is done. If we finish the 7 applications, they are not letting me erase this.
पहले की नहीं एक को सर के साथ
Please write along with me here. Listen, all of you, do one help. Look at the year plan, see our current status.
Infinite line of charge होता है क्या?
सर आप भी कुछ बोलो, मैं भी यही बोलूंगा।
Infinite line of charges plus
Minus.
plus
A.
plus. It goes till infinity.
How long is it?
Okay. So in real life, the scenario is: suppose this pipe is fully charged. Okay. I take a point at this. I look at this point and ask what is the electric field. It is in effect the same scenario because this point is so close. For all practical purpose, this is like an infinite line of charge. Got it? So infinite line of charge for deriving it makes it easy if you consider it as
Where is
infinite,
the
right?
point of interest?
The point of interest, we'll take any point here. So point P. So now, can you imagine or predict the Gaussian surface, how it will look like?
Yeah.
Why not?
Oh, shit.
You need a symmetric surface. Which
This will be the
surface is
diameter.
symmetric to this?
So this will be the diameter which touches
Sphere?
ellipse. So ellipse.
No.
नहीं बन सकता।
Cylindrical.
Oh yeah.
So I take a Gaussian surface like this.
हाँ, sphere तो हो नहीं सकता.
It should be
So all number ऊपर है.
You were हमारा center. क्या दो condition थे?
Wait, point of interest has to lie.
So it is a cylindrical surface. Listen.
Symmetric about the charge area.
Yes. So you can't have a Gaussian surface which is infinitely long. You can't enclose an infinitely long object. So you will have a finite size only Gaussian surface. Now here one point you need to understand. The Gaussian surface cannot have any discrete charge located on its surface. Because electric field at the location of a charge is not defined. Why is it not defined? Because electric field is kq by r squared. If you look at a point which is on the charge, r will be 0, electric field will go to infinity, which is not defined. But here you will ask, then what is happening here?
ये
But
point
this
ये
is-
point of P है, right?
No, I am saying the Gaussian surface is like this, no?
Yeah.
It's a cylinder, closed surface.
Yeah.
So the top surface and bottom surface will cut through the line of charge. So you will ask, if I just know I said Gaussian surface should not have any charge located on that surface. When I say point P, it is not a charge, it's a point in space. But what about here and here? Some charge seems to be located. So the difference is this is not a discrete charge. This is part of an infinite continuous line of charge. That is allowed, but not separate random charges. So suppose I have a positive charge here, some negative charge
So
here.
no charges are allowed to be present on the Gaussian surface.
Yes, but if they are part of an infinite distribution of continuous distribution of charge, that is okay.
No charges are.
No discrete charges are allowed on the Gaussian surface. So I will also write it so because it's an important point. No discrete charge can be present on
Eraser दे दे.
Gaussian surface. See, I cannot have a separate point charge located on the Gaussian surface. But the Gaussian surface can cut through a continuous distribution of charge. That is allowed. Okay? Distribution of charge. That is allowed. Okay, now you see here how this symmetric Gaussian surface helps us to find the electric field at point P. Every time we use the concept of symmetry, it comes to our rescue. See here, if this is an infinite line of charge, is this point different in any way from this point?
No.
No, right? With respect to infinite line of charge, this point and this point are all the same. There is no difference. You cannot identify anyone. You cannot differentiate this point from this point with respect to infinite line of charge. So, if you cannot distinguish these 2 points, the electric field at this point and this point, can they be different?
No.
They should be same. Agreed? And you know that the positive charge will repel everything. So what direction can the electric field have so that you cannot differentiate these 2 points? Exactly away from the line of charge. The electric field at this point has to be like this. Here also like this. Here also like this. If it is not, if you say it is like this, then your question will be, why not like this?
Because they cancel out, na, these ones.
If it is like this, why can't it be like this? The reason it can't be like this because you have equal charge above and equal charge below. So why should there be a priority towards lower side?
Exactly.
There is no preference for a lower side. It's symmetric up and down, infinitely up, infinitely down. So the only option is exactly perpendicular to the line of charge. Got this?
It cannot go towards.
We cannot go towards because it's repelling. It's a positive line of charge. Huh? Electric field has no option but to be perpendicular to the line of charge. The reason is, if you say electric field is in this direction, what is the justification you can give? If it is in this direction, that means there is more positive charge above this point than below this point, so that they are giving a push downwards. But how is it possible? You have equal charge above and equal charge below every point because it's infinitely long, both ways. Are you getting it? So if they are equal above and below, then the net electric field has to be like this only.
So,
got it?
they cannot be above and below because
Is P a charged particle?
Yes.
Is P a charged particle?
P is a point in space. There is no particle there. When you want to find electric field at a point, you will take a temporary positive charge, keep it there and see what force it feels. You will find that you will feel a force in this direction. That gives you the direction of the force. Direction of the electric field. If you divide that force by the charge, you will get the electric field magnitude. Clear? So now we know electric field everywhere on the curved surface area is perpendicular to the area. So the dA vector is like this. dA vector is like this. Electric field vector is like this. So the angle between them is 0 degrees. Agreed? Now what about the top surface and bottom surface?
They won't be counted.
The dA vector will be like this.
They will be counted.
What? They will be counted. You have Gauss law when you apply. It tells you the total flux through the closed surface area. Entire closed surface
Sir,
area.
but it's not a closed surface area because it
It
goes.
is a closed surface
No,
area.
because the line of.
So it is enclosing some charge, not the entire infinite line of charge.
But aren't we taking it for infinite line of charge?
Infinite line of charge is present, okay. What Gauss law says is electric field at any point on the Gaussian surface, okay, it obeys Gauss law means the total flux through that Gaussian surface. Listen, the flux through this Gaussian surface depends on the charge inside this Gaussian surface. It does not depend on the charge outside this surface. Using that concept, when I find the electric field here, it's a fact, electric field is that value only here. It cannot be any other value. You're getting it? So that's the trick. So here the area vector is downwards.
90.
But what is the electric field direction on this surface? At this point, what is the direction of electric field polar?
So,
Very good. So here also electric field is like this.
Ordinary DA ऊपर है.
अरे वो surface
Here is perpendicular to the surface.
circular surface.
So here also electric field is like this. So what is the angle theta here?
90.
Konark.
So 90.
Very good.
Cos 90.
And what is the theta here?
90.
90. So now let's apply the Gauss law. Flux through the entire surface is equal to closed integral of E dot dA, which is equal to closed integral of E dot dA. This is like let us say integral over the curved surface. Let us call this curved surface, and let us call this surface 1. Let us call this surface 2. Okay? Plus integral over surface 1 plus integral over surface 2 so these two will be 0 because the theta is 90 degrees, cos 90 will give me 0. So the flux through the top surface and bottom surface will be 0. This is top surface.
So इसके नीचे C क्या लिखा है?
This is bottom surface. Curved surface. This is curved surface. In curved surface, every area point which you take, the electric field and the area vector will be parallel to each other. Every point on this curved surface, electric field will come out, area vector will come out in the same direction. So the theta is always 0.
So in the surface 1 and 2, sir,
Yeah,
why is the electric field
0.
perpendicular, sir?
See, electric field is due to this line of charge.
Yes, sir.
Every point on this line, every point is equivalent to each other because it's infinitely long. There is no central point. Every point is a center point. So that means everywhere the electric field has to be outwards only from the wire. It cannot have any vertical or downward component because if it has a downward component, that means the electric field, electric charge above that point is more. It is not true. Any point you take, there is equal charge above that point, equal charge below that point. So both will contribute same electric field component up and down. So vertical components will cancel out. You will have only horizontal components left. So everywhere you take, electric field has to be horizontal only. It cannot have vertical component.
So in the objective of the shape, sir,
Object meaning
this cylinder,
the Gaussian surface.
the surface, sorry.
Okay.
So the electric field is horizontal, but at this point, sir, it would be 90 degrees. So area vector would be 90 degrees to the electric field. Sir.
Listen. The line of charge is vertical in my diagram.
Yes, sir.
Cylinder is also vertically kept. So the curved surface area is parallel to the line of charge. Curved surface area is parallel to the line of charge.
Right.
Electric field lines are coming, see, it's like a circle, right?
Yes, sir.
So electric field lines are going like this.
Yeah, that's what I mean.
Okay. Everywhere the area vector is also going in the same direction.
Fine, then.
Area vector is also in the same direction. So always area vector and electric field vector are parallel to each other. Are you getting it?
Yes, sir.
So that's why E dot dA is always going to be EdA. So this will become EdA because dot product, the vector is removed as E dot dA is E dA cos theta. Cos theta is 1, so it becomes EdA. And every point on this curved surface is same distance from the line of charge.
Yeah.
So magnitude of E is constant. So E will come out
is a constant
integral of dA, the curved surface.
2 pi r h.
So curved surface area is
2 pi r h.
2 pi r into L. So let us say the length of this cylinder is L. And we will define one concept called lambda, is charge per unit length. That means coulomb per meter. It will be in units of coulomb per meter. Lambda is the charge per unit length. This is infinitely long. So 1 meter length if you take, it will have say 10 coulombs. So charge per unit length is lambda. So if you have L length of charge if you have L length of the line of charge enclosed by this Gaussian surface, what is the Q enclosed? Yashasvi will tell us. Lambda coulombs per unit length is the charge density. Your total length is L. So what is the charge of this length? It has lambda coulombs per meter. You have L meters. So how much charge is enclosed by this Gaussian surface? L lambda. So the total flux is, so you have E is a constant, and then the curved surface area integral is, total curved surface area is 2 pi r into L. E multiplied dot मतलब multiplication.
cos theta का हो गया ना
I'm just saying that it's multiplied. E into 2 pi rl is equal to by Gauss law Q enclosed by epsilon naught, right?
So why are you taking only the curve?
These two got cancelled to zero, no? So this is equal to Q by epsilon naught, Q enclosed by epsilon naught, which is equal to lambda L by epsilon naught, which implies electric field is lambda L, no, L will cancel out. So lambda by 2 pi r epsilon naught. L will cancel out. And the direction would be along the r cap. Do you get it?
So one second.
Direction will be along the r cap. Where r cap is like this, radially outwards. Direction of electric field will be radially outwards. So given the direction as r cap, unit vector along the radius.
So what is
Yes.
why not you first I'm asking this? Why not you have your electric field? Like you have it as it outward, right?
Yes.
Why not you have it as it?
Okay, see here, I'm again explaining it.
There's no justification, right?
There is a justification, yeah? Come on. Without justification, how can I say anything?
For this direction. For this direction, there's no justification.
For that direction, you cannot justify it. You'll be wrong. See here, if you say electric field is like this, at this point, at this point, if you say electric field is like this, that means that the charge which is below this point is more stronger than the charge which is above this point. That's right, it's pushing, that's right. But how is that true? It's an infinitely long both sides. So you have equal above and below.
So they cancel out.
So their vertical contributions will cancel out. So you'll be left with only this, not this.
So why don't the horizontal components cancel out?
Horizontal components will only add up. See here.
But
This,
then
look
it
at this diagram, necessary. This will push it like this. Okay? Same distance below you take from here.
Yeah.
This will push it like this.
Yes, sir.
These two are equal. They will have x component like this. This will have x component like this. Y component like this. This will have y component like this. These two will cancel out. These two add up. The thing is, as you go towards infinity, the contribution will become smaller and smaller in magnitude because it's farther and further away. But the x component will still keep adding. But it will get smaller and smaller so that it will still give you finite electric field. See, you might have thought if it's an infinite line of charge, electric field should become infinite. You would have thought like that? If charge is infinite, so the electric field is still finite. So even though the total charge is infinite, the electric field is not infinite because it gets further and further away from the point P, so that its contribution becomes smaller and smaller and smaller, so that you get a finite electric field. And it makes sense, it's proportional to lambda. So more the charge density, more the electric field. And it falls off with R, the distance from the line of charge. The further you go, the lesser the electric field. But it is falling off as inversely proportional to R.
So can you have your electric field in this direction?
Of course,
Then
it is radially, see, it is radially outwards.
Why would they get cancelled
Why will they get cancelled also?
Okay, the electric field here, how will it cancel the electric field here? This is a different point, this is a different point. How can they cancel out? If it's like saying you are standing here, one more boy is standing here, I push him that side, someone pulls you this side. Will these two forces cancel out? Suppose I pull you this side, I pull him this side. Can my two opposite forces cancel? Each of your forces, the forces acting on each of you, they are acting on different objects. How will they cancel out? They have to act on the same object. Here it's this way, here it's this way. It's different.
Two different objects.
Two different objects, two different locations. They cannot cancel. Clear? Next, can you predict what is the third application? From point you move to line. What is the next step?
Cube.
Cube is 3D. First sheet.
Sheet.
And will it be finite or infinite?
Finite.
Infinite. Here we did infinite, there also infinite.
Infinite.
Finite is complicated. If you have a finite charge, till here it will be like this, then here it will go like this, right?
Yeah.
So this will become complicated for us. So that's why we don't do derivation for finite charge distribution. We do infinite charge distribution. Because then we can take the use of symmetry and say electric field is only horizontal and we can find out. So now we will take infinite sheet of charge. Now how is this result useful to us? It is useful to us provided we take a point whose distance r is very small compared to the length of the charge. Then it follows this approximation. Are you getting it?
R is very small compared to.
See, we have derived this result for an infinite line of charge. But still you can apply it even for this line of charge. Provided the r is very small, like here. If r is here, this formula will fail for this object. Are you getting it? If r is here, compared to r, this length is so huge, it is like an infinitely long line of charge, like that. So deriving this is easy. But deriving for the actual length is difficult. You getting it? So in physics, such smart things we do. We derive it for a simple case mathematically and then apply it under valid conditions for real life. Okay, now infinite sheet of charge. Yeah, you will at least get some physical, some mental orientation, no, in the start. Then we will continue where we left off. So those who missed yesterday's class, please watch the video so that you are on track with the syllabus. Otherwise it will be difficult for you. And practice questions also. Okay. So now what we do is we take a different
What is infinite sheet?
Yeah. Electric field due to infinite sheet of charge. So for a line of charge, we had a charge density which was linear charge density. So charge per unit length. So for this it will be surface charge density. Sigma is surface charge density.
उसके लिए क्या था सर?
Linear charge density. Linear is length. So it will be coulomb per meter square. Okay, so we'll continue this next class.
सर एक मिनट पिछला फॉर्मूला था उसमें व्हाट वाज
R cap is a unit vector along the radius.